Today, we're going to be mathematical detectives. Our mission? To follow the clues hidden deep inside a single physics equation, an equation that, when you push it to its absolute limits, just completely breaks down, and in doing so, reveals a puzzle that points to a truly bizarre new state of matter. And the question at the heart of our whole mystery is this: what happens when you get colder than cold? What happens when you get so close to the absolute limit of temperature, absolute zero, that the familiar rules of physics start to, they start to bend, and things get really, really weird. Now, our whole story revolves around a very special type of particle, bosons. You can honestly think of them as the social butterflies of the particle world. See, unlike most particles that need their own personal space, bosons are totally happy to just pile into the exact same quantum state all at the same time. And this weird ability to clump together, that is the key to everything we're about to uncover. All right, so every investigation needs a starting point, right? A blueprint. And for us, that's the fundamental equation that tells us exactly how a gas made of these boson particles is supposed to behave. And here it is, the Bose-Einstein distribution. Now, don't worry about all the symbols. What this equation is actually telling us is pretty simple. It's our rulebook. It says, for any given energy level you can think of, here is the average number of bosons you should find there. This is our first and most important clue. But of course, a real gas has countless energy levels. So to get the total number of particles in our entire system, we'll call that N, we have to add up the particles from every single possible energy state. And in physics, when you add up a basically infinite number of these levels, that sum turns into something called an integral. This gives us our master equation for the whole shebang. Okay, so first things first, any good detective tests their tools under normal conditions. So let's see what our blueprint equation predicts in a familiar, high-temperature situation. We need to get a baseline for what normal looks like. Now, at high temperatures, the math can get a little messy. So physicists have this standard trick they use called a series expansion. It's really just a clever way of approximating the equation to get a much simpler, more useful result when you're looking at a specific case, like high temps. Think of it like making a simple sketch from a super complex blueprint. And what that approximation tells us is actually really cool, because it shows you what's happening physically. The result says that the quantum wavelength of each particle is teeny tiny compared to the actual space between them. So, in other words, they're just like these little, distinct billiard balls, flying around and almost never feeling each other's quantum weirdness. So, hey, our first test is a success. The equation predicts that at high temperatures, this special gas of bosons acts, pretty much like any normal gas you'd think of. It passes the sanity check. Our blueprint seems solid. For now. But this is where our detective story really kicks into high gear. Because when we leave the safety of high temperatures and we start cranking that coldness dial way, way down, a reliable old equation starts to show a crack. A paradox starts to bubble up. This is the big one. As we get closer to the coldest temperature imaginable, a place where quantum effects should be the only thing that matters, what does our equation tell us is going to happen? Let's push this thing to its absolute limit and see what breaks. Okay, let's examine the evidence at low temperatures. On the left side of the equation, you've got the particle density. That's the total number of particles, N, inside a certain volume, V. Now, this number has to stay constant, right? We're not adding or removing any particles. But on the right, we've got a bunch of stuff that depends on temperature. And right here is where the puzzle pops up. The clue is hidden in that function, that G on the right-hand side. As we make things colder and colder, this function gets bigger. But it has a hard speed limit. It can never be greater than about 2.612. It hits a mathematical wall. And that creates a completely impossible problem. Think about it. If the right side of our equation has a maximum value, but the left side is a fixed number that's bigger than that, the equation just doesn't work. It breaks. As the original notes put it, the only way the math holds up is if particles just disappear as things get cold. And that's absurd. Physics doesn't just let matter vanish into thin air. A paradox like this in physics almost always means one thing. You've overlooked something. The problem wasn't with the universe. It was with a tiny, subtle assumption we made in our math. And that leads us to the big revelation. Here it is. This is the smoking gun. Remember when we turned our sum of all the energy states into that smooth integral? Well, a little mathematical quirk in doing that made us completely ignore the single lowest energy level, the ground state, where the energy is literally zero. We basically made it invisible to our own calculation. Now look, at high temperatures, ignoring one state out of trillions upon trillions, it's no big deal. It's a rounding error, who cares? But as you get incredibly, incredibly cold, particles don't have enough energy to be anywhere else. They all want to fall into that single lowest state, the one we just ignored. That one single state suddenly becomes the most important place in the entire system.
This simple little expression here tells us how many particles are in that one ground state, and it reveals everything. As the temperature drops to its absolute minimum, this little variable z gets closer and closer to the number 1. So what happens in that denominator? You have 1 minus a number that's almost 1, that gets infinitely small. And when you divide by an infinitely small number, it means n0, the number of particles in that one state, just skyrockets towards infinity.
And just like that, all our puzzle pieces just snap into place. The missing particles? They weren't gone at all. They were hiding in plain sight, in the one place our math was accidentally blind to. So the solution is actually pretty simple. We just fix our original equation. We keep the integral that counts all the high-energy, excited particles, but we add back a separate term specifically for the particles that are piling up in that special ground state. And with that one correction, the math works perfectly again. The books are balanced. So what does this all mean in the real world? It means that once you go below a certain critical temperature, the particles in the higher energy states basically run out of room. They have nowhere else to go. So they start to just drop out and accumulate more and more of them into that single lowest energy ground state. And this massive macroscopic pileup of particles into one single shared quantum state, well, it's not a gas, it's not a liquid, and it's not a solid. It's something else entirely, predicted just by fixing that little crack in our equation. It's a fifth state of matter, the Bose-Einstein Condensate. And it just makes you wonder, doesn't it? Our whole journey started just by noticing when an equation didn't quite make sense. So if an entire new form of existence can be found hiding in a simple mathematical oversight, what other incredible secrets about our universe are just waiting to be found in those little places where our numbers, just for a moment, don't quite add up?